Hello, in this video I'm going to run through stellar magnitudes. I don't think this is going to take very long. It's fairly straightforward, but it's also very important. This is how we describe the brightness of stars, whether in the night sky, so their apparent brightness, or the actual brightness of these stars. So we just need to be familiar with the terminology, really. So the things that we're going to be unpicking here are apparent magnitude. So that's how something appears to look in the sky, how bright it seems to be. Then we've got absolute magnitude, and that is then normalizing all of this so we can actually compare objects then on the same scale. So we're taking away the distance from the Earth to the object and setting them all at the same distance. And then we've got bolometric magnitude as well, which is worth knowing what it means. So for absolute apparent magnitude, so this is where people started off. I mean, the Greeks, ancient Greeks, they started dividing up stars into 6 categories of brightness. So they went from 1 to 6, and this has sort of stayed as the bit of the legacy of what we got nowadays. 1 to 6, with 6 being the limit of what the naked eye can actually see in the night sky, and 1 being the brightest ones. And they divided these stars up into these 6 categories, going from brightest to dimmest. And this has had a sort of the hangover of this into the modern system. Now, in the middle of the 19th century, Norman Robert Pogson, he came up with a logarithmic scale for this. He tried to make it a bit more formal, a bit more rigorous for what was happening. So he was saying, well, a first magnitude star. So if you're in that first category, it'd be called first magnitude, and that will have 100 times the brightness of 6th magnitude. And then we've got this logarithmic scale going down from 1 to 6. So as you move from one step to the next, you've got a multiplier, because we've got 5 jumps, haven't we? 1 to 2, then 2 to 3, 3 to 4, 4 to 5, 5 to 6. So these 5 jumps have got to end up multiplying up to 100. So you've got the 5th root of 100 is the multiplier from one magnitude to the next. That comes out at around about 2.5. So that's the multiplier. If you've got a second magnitude star, then the first magnitude star will be about 2.5 times the brightness of the second magnitude star. So this is how you can then compare these apparent magnitudes, what it looks like to us from the Earth looking at these stars. Now, of course, that brings in some problems in itself, because you can say, okay, how it looks like to us from the Earth. Well, where is it in the sky? I mean, things look brighter in the sky if they're straight up than they do if they're at the horizon, because they've got to come through less of the Earth's atmosphere if they're higher up in the sky. So that's one thing you need to take into account when trying to calibrate all of this. Where is the object in the sky? Then, of course, you've got the issue of, well, what wavelengths are we actually looking at? We know that we've got the visible spectrum, but, well, where exactly are we setting the ends of these? What amount of light are we considering inside this calculation of brightness? Again, that isn't obviously and clearly defined, so we have to make a decision on that as well. So then it's okay, well, we try and find some stars that we think we can measure consistently, that are in a good location in the sky, and our measurements aren't changing around too much. So let's get some calibration stars, essentially, that we can define as well as we can, and then we'll use these for comparison with other stars. So you'll set up a calibration star. We'll know something about an experimental setup that will record the light coming in from that star, say how much there is in a certain part of the electromagnetic spectrum, and then if we've got another star, we can run it through exactly the same experimental setup, hopefully at a similar position in the night sky, under similar observing conditions, trying to get everything as close as possible to our calibration conditions in terms of experimental setup, observing conditions, and position in the night sky. If we can replicate that, then we can say something about the apparent magnitude of this other star with reference to the calibration star. This, of course, has a number of issues when it comes to determining the actual brightness of a star. And this is what we're trying to get in absolute magnitude. So we're trying to remove a number of things from the equation in this. So in apparent magnitude, we don't care about how far away the star is. So here we're saying, well, what if all of the stars were at 10 parsecs? Let's try and get everything to that distance and then say how bright they would appear. Another thing that we want to deal with in absolute magnitude is what's referred to as extinction. This is essentially stuff getting in the way of a star. So a star might look dimmer to us, it might look fainter because there's a dust cloud in the way. There might be some interstellar gas or cloud or something which is between us and the star, which is removing some of the light. So it will appear fainter, but in terms of absolute magnitude, we want to see if we can factor that out somehow and just talk about the star. We don't want to talk about things that are in the way of the star. So absolute magnitude is, it's not easy. That should be fairly obvious from those two descriptions of what we're trying to do, that that's not an easy process. How do you determine how much light is being removed? We need to know how far away an object is in order to say how its brightness will change if you move it to 10 parsecs. And we've already discussed the difficulties in getting stellar distances. So determining absolute magnitude is conceptually straightforward. It's easy to understand what we're trying to do, but in practice, it's a very difficult thing to achieve with any accuracy. So, and just a reminder again on distances, 10 parsecs, this is going to be around about 33 light years, just a little bit less. So that's apparent magnitude and absolute magnitude. The other one we've got is bolometric magnitude, which gets spoken about a lot, particularly when you start talking about hot stars, because this is then including all wavelengths. So this is all of the light that's coming out, all of the energy that's coming out of a star. So we don't have this issue with apparent magnitude where we're just saying, well, what does it look like in the sky? How much visual light are we getting? That's apparent magnitude. Bolometric magnitude is saying, right, well, all of it. We want the whole lot. We want everything underneath the curve on this stellar spectrum. So this is a real difference then when you've got these super hot stars that have got these massive peaks in UV and beyond. So we'd just be looking at, well, what's the area under the curve here, pretty much, for your apparent magnitude. What have we got in the visible part of the spectrum? Well, look at all the stuff we're leaving out over there. We're leaving out the big part of the curve for these super hot stars. It's not like that with the sun, where you might have a spectrum which is a bit flatter. It's peaking in the visible. You're getting a good chunk of the actual output of the star in the visible part of the spectrum. So you're not losing as much, greater percentage on a cooler star as you are on the hot stars. So bolometric magnitude of hot stars can be just huge. So that's another one that comes up in discussion as well. So looking at how these things vary then, the sun obviously ridiculously bright in the sky. It's got an apparent magnitude of, I don't know, minus 26, is it, or something like that? It's been a while since I've looked at that, but it's in that sort of order. Very, very bright. I should have said earlier on, although we've got this 1 to 6 that they started off at, well, you get stars that will go down to 0 or even -1. Sirius, the brightest star in the night sky, is about -1.4. So, we're going outside of this 1 to 6 scale. Plus, of course, with telescopes, binoculars, things like that, we can go up to higher numbers than 6. Even with a backyard telescope, you can start getting up to 11. So you don't need a lot, or even beyond if you've got big telescopes that amateurs use in their back gardens. But just a modest telescope is going to take you a lot further than 6. But with the sun, if we see it at some ridiculously negative magnitude because it's so close to us, But if we do absolute magnitude for the sun, then you're looking at sort of, I don't know, 4.5, 5, something like that, 4.5 or 5. So that would be the absolute magnitude of the sun. If we go to our Orion classics here and we look at Betelgeuse and Rigel, so the two bright ones in Orion, they got similar apparent magnitudes. I mean, Betelgeuse varies a little bit. It had a blip a couple of years ago, actually, but that's got around about 0.5 apparent magnitude. Rigel about 0.13 apparent magnitude. But when it becomes absolute magnitude, then you're getting on for -6 for Betelgeuse, about -5.85. And then even brighter than that for Rigel, so -7.84. So yeah, you're getting some serious absolute magnitudes there of how bright they would be. And of course, we expect this. These are supergiants. So you look at the luminosity; they've got big radius. Rigel's really hot as well. This is a B-type star. Betelgeuse isn't. It's an M-type star, so that's a lot cooler. But so the temperature doesn't help as much with the luminosity as Betelgeuse. But Rigel, big and hot, so high, very high luminosity. So that's just the sort of key ways that we're talking about magnitudes here. So when we're talking about stellar magnitudes, we're talking about brightness, where this is linking into luminosity. I know we describe the luminosity in a different way. We're talking about wattage and such like, and this will be fitting in with the bolometric magnitude a lot more than apparent or absolute magnitude, because we're wanting to look at the wattage over the whole electromagnetic spectrum for a particular star. But all of these things are pointing towards the same property of a star, whether we're talking about magnitude, brightness, luminosity. They're all pointing in the same direction, just with subtle variations in context, and that's why we're using different terms in different contexts. But we'll see that we can put these magnitudes onto see them on when we talk about the Hertzsprung-Russell diagram, which we're finally going to be able to do in the next video. Then magnitudes can tap into that as well, but mostly we're going to be talking about that in terms of overall luminosity of stars. So yeah, that'll be coming up in the next one. We're finally there for Hertzsprung-Russell diagram, and then moving into stellar life cycles and evolution.